Hello and a warm welcome back. Forgive my voice, I've got a bit of a cold, so I'll be a bit nasally and twangy. Anyway, today on the bench are the EL84 monoblocks that were previously featured in the video, where I tried to get them going and try to find out what the output transformers were. Since then I've been doing a bit of digging and put a post on a forum that I'm a member of. And as far as we can discern, these were made by the Armstrong and Wireless and Television Limited company, who were based in London. They think it was formed, from what I can find out online, about 1926, and they were on the King's Road in Camden Town in London, in England obviously. But after that they moved to Holloway. These amplifiers, I think, sort of date from about 1954-63, maybe a little bit later. Because by the end of the 1970s, this company had stopped making amplifiers and things like that. The chassis is definitely the same as some amplifiers that Armstrong made, particularly the A20. There was a few versions of this. Some had 4 6P25 output valves. Others EL84s. These ones, although they use the same output transformers as the A20 etc, and the same choke, noticeably this CH125, we don't really know what these are. They could have been made for a one-off for a jukebox or a PA system, I'm not really sure. And I think since then somebody's changed the circuit once again. The output transformer that consternated me like last time, when it was used in the A20 and what have you, was configured for 16 and 34 ohms, which sort of lends itself to a PA amplifier, you know, like 2 series 16 ohm speakers. That would make sense. Yeah, so bit of a conundrum, these ones. Ian, whose amps these are, sent me over some new output transformers, and these are 6K6 primary impedance output transformers, and these work a lot better with an 8 ohm load. So as you can see on this one, I've fitted the output transformer, which involved cutting out a section of the chassis. They just fit in there, and as you can also see, I've changed the output section, putting in bigger cathode resistors and a bus bar for the 2 output valves. When I changed the valve bases, I found, as I mentioned previously in the last video, that they were using the chassis for the ground. However, they hadn't removed the paint on the grounding tab, as it were. So what I've done, I've sort of modified things a little bit and then put this big sort of bus bar in there and then connected that straight to the first capacitor ground. I've also changed the valve bases because the last ones, as I think I mentioned, had the sort of tuning fork type pins. This is a tuning fork type pin. As you can see, it only grips the valve base at 2 points. And so the ones I've used have got this cup type valve pin, which is a lot better. However, the valves are still not really grip really firm, and so what I did, I measured the valve pins, because these are Chinese EL84s, but all I could find really was that they were about 1 thou thinner than sort of old valves, you know, so I don't really know if that would make a difference. As you can see, made a few changes. It was a bit tight to get the output transformer in there around all the other circuitry. Got rid of the other potentiometer over here, took off that 1/4 inch socket, put the RCA in there instead, and I've tried to improve the grounding scheme a bit by putting the ground to the input. As you can see, I put the grounding point for the input of the RCA right next to the grounding point of the pentode section which forms the voltage amplifier, and well, in an effort to improve the noise floor. However, I seem to have screwed up on that. Changing the output valve bases has cleared up the fault we had with the control grid floating about all over the place. So as you can see, that's sitting at 0.13 volts, and the other one sitting at about the same voltage. Cathode voltage about 11, oh you monkey, about 11 volts, just locked onto the what's it there, and on the other one just under 11 volts. So let's have a look at the AC conditions now. Just turning the input up. So as you can see, at 100 millivolts AC, the signal is being modulated by that noise or hum, whatever it is, and so that's not very good. You can see it's still dancing about a bit. I'm not quite sure why that is. For some reason my scope's playing silly buggers. Here we are the next day, chucking it down outside, so forgive the noise. Probably arse end of the storm that they were having, storm Beelzebub or whatever. Anyway, we're looking at this. There we go. So this is with no input, and this is just parasitic oscillation. That's 27.2 kilohertz, 3 volts. Now what I'm going to do, I've got a flying lead here, one end to ground, this is the other end. I'm going to be touching it to the pentode control grid, which is here. You see we've got this big long wire, which I did thought was a bit iffy. I'm not sure if it's coming in and it's picking this up from outside or what. There we go. And as you can see, that kills the oscillation. I'm just going to touch it as well with a wooden stick. So all I'm doing is tapping the capacitor, that big long lead to the capacitor, and as you can see that affects it. So what I shall do, I'm going to unsolder this lead and see if that makes any difference. As you can see, well you can't see, me just touching the chassis here affects it. In fact that just stopped it, that is stopping it, which is, yes, I think it's coming from the outside. Let's see if it works if I touch it here. Yeah, it does. So we've got to do something about this long lead here. Right, I've put a piece of shielded cable in there, terminated in this 100N capacitor which goes to our control grid. And as you can see, all things are quite silent. I'm turning the volume up now. We have no oscillations. Right, that's the highest amplification, as it were. Turn the time base, and that is a lot quieter as well. We're now at 20 millivolts peak to peak. Oh no, that's RMS, 20 millivolts RMS. So now we need to try and address that noise a bit more. I want to try and get that down to a few millivolts if I can. As you can see, what I've done here is put a 250 ohm potentiometer pot in place of these two fixed 100 ohm resistors across the AC of the heater supply. This is just one I had knocking about, so I won't actually put it like that. So let's have a look at the noise now. Right, 0. What's it, volts. Right, it's actually gone up. What I'm doing is adjusting the pot to get the best reading. Need that going down Whoops, there we go. Just a bit stuck. 77, 59, 32. Right, now we're getting somewhere. We're about back where we started, a bit above. It's about the best I can get it there, about 10 millivolts. Let's have a look at that on the scope. So that's probably playing merry hell with the display because of its frequency. That's at about 10 millivolts RMS, 25 millivolts peak to peak. So a lot better. Okay. Now we're at 700 millivolts RMS, 1 kilohertz, and as you can see there is far less dancing about, much better. I've fixed the humbucker potentiometer in place instead of those fixed 100 ohm resistors. I've also fitted some screen cable here to this feed over from the cathodione phase splitter over to one of the grids of the EL84s. Let's have a look at the oscilloscope and see what's going off. This is a sine wave at about 1 watt. As you can see, we have 0.5% distortion. I'm just going to turn that up a touch. Starts going up at about there, which is 5 volts RMS, or 4 watts. So we've got 0.6% THD at 4 watts. See how much we can get out of it before it starts to clip again. I suspect it'll be about, about 12 watts. Just turn that down. At 10 watts we have 1.4% THD, but this is open loop gain. So let's have a quick look at the frequency response. So this is a 1 kilohertz sine wave at 4 volts RMS. Let's chuck it down to 100 hertz. Right, that's dropped significantly. That's dropped down to 2 volts RMS. So, not good. 10 kilohertz. Feeling a little better there. We're back up to 4 volts RMS. Let's try 20 kilohertz. As you can see, that start to drop off a bit. However, this is all open loop gain. So what I'm now going to do is attach some negative feedback. So as you can see, that's dropped down. Sorry, I took the wrong one there. We're getting oscillation. So where are we then? That's 20k precision pot in there. What did we have before? Okay, we've got 4 volts, and that's dropped to less than 1 volt. So let's see what we get now. We're back on 1 kilohertz. Just see how much we're going to get out now. Okay, we're about there. Okay, we're still getting 10 volts, so we're okay. We're all right. Let's go back to about 2 volts, and let's have a look at a harmonic distortion. It's 0.2% now, so our total harmonic distortion has improved. Let's see if our frequency response has improved. So I've got a figure of 1.3% THD. I'm going to decrease the value of the pot from 20 kilohertz down, and as you'll probably see, that sine wave getting smaller. Seeing how low we can get the THD before it goes unstable. As you can see there, we are down to 0.01%, let's call that. Just compensating by turning the volume control back up. So where are we now? 0.08, and that's at 3 volts. Now let's see how much we can get out of it before it starts clipping. Right, okay, we're still getting 10 volts RMS, so we haven't really lost a lot of power. However, we are getting a lot better distortion level readings. Let's just take that up to 10 again, and let's see what we're getting distortion wise now. So before we were getting 1.4% THD, now we're getting 0.4%, so that's a improvement of what, I don't know, 75%. I'm not very good at maths, but yeah, so that's a hell of a lot better. So rather than show you hours and hours of footage of me farting about testing this, I'm going to cut it there, fiddle about with it, try and get it as best as I can by increasing or decreasing the amount of negative feedback, and then we'll get on to square wave testing, and then hopefully we will wrap this video up. A little mucking about later. I tried tacking in a couple of 100 microfarad capacitors to boost the capacitance on this output stage, on the cathode decoupling caps, from 47U to about 147U. That did improve the low frequency response somewhat. Then I had a look at other sort of suspects that I thought might be dragging the high frequency down, and then looked at this, which was a 102. What's that? That's, oh, canal. Yeah, that's 1,000 picofarads, which I had on the front end, which was obviously rolling off the low frequency response right at the front end. So what I then put in was a 2.2 microfarad capacitor. That improved things a hell of a lot. Then I dug about in the spare capacitors that came off this amp that I took off, and so replaced that 100 picofarads with a 220N capacitor. So as you can see, this is 50 Hertz sine wave, and according to my HB8903B, we are down we are down 0.1 dB. Let's bung it on 20. Where are we? Frequency 20 Hertz. Okay, now we are down about 2 dB, and as you can see, the sine wave's getting a bit horrible, but I think that's down to the output transformer, to be honest. Let's just bung it up a little bit more. Yeah, and as you can see, that is a better sine wave. However, it's jigging about and dancing about, and the reason it's dancing about is because it's being modulated by the 50 Hertz hum noise that we've got present in the amplifier. We're back to 1 kilohertz now, so let's have a look at the high frequency response. We're at 7 volts. We've not lost anything at 10 kilohertz or at 15 kilohertz or at 20 kilohertz. See how we can go. And as you can see, we're starting to get a bit of silly buggery here with the sine wave being distorted. This is with feedback, obviously, and as you can see, if anything, the frequency response has increased. It's starting to peak. So what we shall do, or what I shall do, is when I choose the feedback capacitor, I will hopefully address that and then cut the high frequency response down a little bit, and then that should clear that up. We'll see. I've got the amplifier all ready to test with a square wave. What this is a capacitance decade box. So with this box I can set it to various amounts of capacitance. I've got that in parallel with this 10k resistor, which is a feedback resistor, which has replaced the 20k precision pot that we had in there earlier on. So what I did, I took it off, measured the resistance across that I had, it was about 12k, and then so what I've done, I've just popped a 10k in there for now, and we'll see how that goes. So now, and then what I've got over here, what I've got here is a little circuit that converts our sine wave that comes out of our HB8903B into a square wave. I'll just plug this battery in, and then what I will do is I will put in various frequencies of a square wave and then apply capacitance until we get a good square wave at about 1 kilohertz, 100 hertz, 10 kilohertz. We're trying to get the best square wave response that I can. So this is a 1 kilohertz square so this is a 1 kilohertz square wave, and as you can see, all things are not well. We've got some ringing which indicates low frequency instability, and as you can see from that jigging about a bit, that also indicates low frequency instability. What I'm going to do is untack those 100U capacitors that we've got going across the cathodes on the output stage, the EL84 cathode bypass resistors. So as you can see, that has improved the situation somewhat, although we've still got this ringing. I don't think applying some capacitance on the feedback circuit will do anything. Oh no, I'm wrong. I take it all back. So what I just did there, so what I just did there was to put a bit of capacitance across that feedback resistor. Right, so that is 100 picofarads. That's 200 picofarads, and as you can see, that has improved things a hell of a lot, which has surprised me, because I thought with ringing here that indicated low frequency instability. Maybe it was a high frequency instability. That's 300 picofarads, 400, 500, 600. Right, and I don't know if you saw that each time I applied more capacitance, the rounding here got more. But each time I applied the capacitance, the rounding increased. So I'm going to take that off. That's 5. Oh, and that's just knocked it right into instability. I think I just knocked it in. Okay, so we've got 300 picofarads there. So what I'm going to do now, I'm going to switch to 100. What I'm going to do is switch to 100 hertz square wave frequency. 100. Oh bugger! 100 kilohertz. Pardon me. Frequency 100 hertz. And as you can see, we've got some sloping off here. I will cover this in my testing audio amplifiers. So what we've got there is low frequency roll off, which we knew we'd got anyway. It isn't severe, so I think we can live with that. Increasing or decreasing the capacitance won't, at this frequency, won't make much difference, I don't think, but let's try it anyway. That's 4, 5, 6, 7. No, it won't. So I'll knock it back to 3, and then now what I'm going to do, I'm going to increase the frequency to 10 kilohertz. And as you can see, it's still a square wave, but it is less than perfect. So let's try decreasing the capacitance. So that's down to 200. That's down to 200 picofarads, and that's down to 100. And as you can see, we've got some overshoot and some instability, some ringing. So I'll increase that, and now I'm going to increase it just so you can see what the effect is. So that indicates high frequency roll off. So basically what I am doing, or what we are doing, if we put more capacitance in the feedback path, you affect how the amplifier responds to various frequencies. So I'm going to knock that off. Right, 3. So that's where I had it before. So what you're trying to do, if you do the same thing, once you've found your feedback resistor value by using a potentiometer to improve the harmonic distortion, we then put a capacitor in parallel with that, and then we're trying to find the best capacitance value so that the amplifier responds well at low frequencies and high frequencies. Just for a laugh, let's bung that up a bit to 20 kilohertz. And as you can see, it's not a brilliant sine wave, it's not a brilliant square wave. That's reducing the capacitance down to 200 picofarads. That looks better to me. So now what I'm going to do is I'm going to knock it back onto a sine wave and see how the amplifier tests then regarding frequency response. If you remember earlier on, I showed you the frequency response at 30 kilohertz. And so now we've applied some capacitance to reduce the high frequency response of the amplifier. Let me just increase that frequency to where we were before, which is I think 30 kilohertz. And as you can see, the waveform is a lot better than it was before. We had some increase in the frequency response at about 30 kilohertz, and the sine wave started to distort. Now that isn't the case. It looks a lot better. Frequency, and that's at 40 kilohertz. So what's happening is that capacitance across the feedback resistor is knocking the high frequency response of the amplifier down. That's why you bung a capacitor in there. I hope that all makes sense. If you have any questions, please pop them in the comments. Anyway, right, camera's playing silly buggers, so I think we're going to have to go and do all this bugger again. Anyway, where are we? Frequency 100 Hertz. So as you can see, at 100 Hertz we've got no attenuation of the signal. Same applies for 50 Hertz, and the same applies at 20 Hertz. So according to my readings on the Duflang Mahungalhasha, we are just shy of 1 dB down at 20 Hertz compared to 1 kilohertz. Now let's go up. Frequency 10 kilohertz. Are you alright there, camera? You happy? You swine. And at 10 kilohertz we are still cushy, and I'm reading 0.15 dB down. Let's go up higher. Frequency 20 kilohertz. Ooh, we're dropping a bit, but remember, this is peak to peak. We're still okay. At 20 kilohertz we have 0.43 dB loss. Frequency 50 kilohertz for a laugh. And at 50 kilohertz we're still less than 3 dB down. We're only about, well actually specifically we are 1.9 dB down. So I think that's bloody excellent frequency response, don't you? Frequency kilohertz. Right, let's knock that off and then let's have a look at the harmonic distortion. Okie dokie, we've got 2.5 volts. Let's just whack that up a bit. Sort me dude alright there. Alright, hold on. Let me just sort me doings out. Right, I've got 4.79 volts RMS at 1 kilohertz. Let's have a look at the THT. Ooh, yeah, spanker. We are 0.07% THD, which is rather, well, to be honest, yeah, I think that's bloody good. Let's have a look at that at 20 Hertz. Oh, tits on a fish. Sorry. Press the wrong buttons. I'm getting carried away here. Frequency 50 Hertz. Don't go mad, Dad. Right, at 50 kilohertz, what we got? Sorry, I got a code. Right, at 50 kilohertz we are still less than 1% THD. Well, it's 0.4 as you can see. At about 1 watt. Right, I'm just going to go up and then we'll go higher in amplitude. Frequency 10 kilohertz. And at 10 kilohertz we're still less than 1% THD. You can see the reading, you don't need me to say it. So let's go all the way up, shall we? Sort my oscilloscope out. Right, we're getting up to full power now. Sine wave looks lovely. THD, and it's still less than 1% at whatever that voltage was. Let's go down in frequency. Frequency 20 Hertz. Ooh, that's a bit oh, and if you look at the screen, we've got all sorts of madness going off there. What is going off? Hold on, let me just, ooh, that is interesting. Okay. Right, this is with the scope's frequency time base set high, going lower. So you can see that. I still think we've got a bit of low frequency instability there. But as I turn that up, 20 Hertz at 8 volts isn't looking very good at all. So I thought we was doing really well, everything was fine. Frequency, but I can tell you, I think with confidence what that was the output transformer saturating at that output power at that lower frequency. Now I've knocked that up in frequency, everything is good. Right, we're still at 8 volts RMS and we're still less than 1%. So all in all, the amplifiers turned out well, those few modifications that I've made. There's still some work to be done, just sort of tidying up loose ends and what have you, but I am really impressed by the frequency response and the very low total harmonic distortion readings. As you can see, there is a lot of time that you have to go through to test your designs and your amplifier builds. I hope that gives you some idea of, you know, what's involved, and that it will help you to build your own valve amplifiers, tubal amplifiers in future. I've edited about half the amount of footage that I've actually taken, so yeah, there's a lot of work involved. Right, I'll shut up rabbiting, let you get on, go and get this video edited, and then I'll see you all next time. Thank you all for watching. Ta-da for now.